All right, for the first problem, the directions say use the rules of differentiation to find the derivative of the function. So it's important to pay attention to what the directions say and what you're supposed to do. That's why I keep including them here. That just means find the derivative, and you can use the shortcuts. So the derivative of cosine is negative sine. The pi is just a constant. So when I use my derivative rule, this will become negative pi sine of t, and that's it. For the next one, you might want to rewrite the y equals, so 1 over x is x to the negative 1. You don't have to rewrite it. It just makes power rule easier. Now, be careful with false equivalencies. This is a big thing on the AP test. The next thing I'm going to do is take a derivative, and it would be wrong if I just said equals and then started doing the derivative. You've got to name it dy dx or y prime, but don't just start putting a string of equal signs down because the derivative is not equal to the original function. All right, so power rule says this is going to be negative x to the negative 2. The derivative of sine is cosine, so minus 3 times cosine x. And then we just always should be in the habit of rewriting negative exponents. But beyond that, you don't really have to get common denominators because we're just finding derivatives. We're not setting them equal to anything, so there's no reason to combine. Find the derivative of the function. So here's this function. Remember, it's not correct to take the derivative of the top and the bottom. Instead, what you should do anytime you see a rational function where it's just a monomial in the denominator, you should divide. So x cubed over x squared is x. Minus 6 over x squared, I'm going to write that as minus 6x to the negative 2. Since nothing canceled, I'm just rewriting the negative exponent. And then again, I want to make sure I call the next line f prime of x, and I don't just write an equal sign. So the derivative of x is 1, because you get 1 x to the 0. Negative 6 times negative 2 becomes positive 12, x to the negative 3. And then again, I'll just rewrite my final answer without negative exponents. This next one has a bit more work to it. It says determine the points, so make sure that you get x, y points. You don't just stop at x, if any, at which the graph of the function has a horizontal tangent line. So a graph will have a horizontal tangent when, in this case, dy dx or y prime, whatever, is equal to 0. So that means that I need to first find an equation for dy dx so that I can set it equal to 0. So the derivative of radical 3 times x is radical 3. The derivative of cosine is negative sine, so this is going to be minus 2 sine x. And they're just keeping us on the interval 0 to 2 pi. So you only have to think about one trip around the unit circle. We're not doing infinitely many answers. All right, so I want to set dy dx equal to 0, so I'm just going to sub in a 0 there. And now we're solving a trig equation, so we have to remember how to do this. Isolate the trig term, so subtract radical 3, divide by negative 2, which will come out to positive radical 3 over 2. And then we have to remember, when is sine x equal to radical 3 over 2 around the unit circle? So you should be in quadrants 1 and 2. And the quadrant 1, the reference angle, is pi over 3. The pi over 3 version of that angle in quadrant 2 is 2 pi over 3. Make sure that you're always answering in radians and not using degrees. So again, I'm not finished at this point. I almost boxed in my answer, but remember it says determine the points at which the graph has a horizontal tangent line. So I now know the two x coordinates where we have horizontal tangents, but I need to plug them back into the y equation to see what the y coordinate is. So I think in my work I just called it like y of pi over 3. So let's see. So back in the original equation, that's radical 3 times x, which is pi over 3, plus 2 times the cosine of pi over 3. All right, now remember, if the sine of pi over 3 is radical 3 over 2, cosine of pi over 3 is 1/2. So if I want to clean this up a little bit, I'm going to put the pi out in front so it doesn't look like it's under a radical. So pi times radical 3 over 3 plus 2 times 1/2, which is just 1. And you can leave your answer like this. Or I did simplify it because if this were a multiple choice problem, they almost always get a common denominator and put things into one fraction. So just so you're aware of that. So the ordered pair, one of the ordered pairs where there's a horizontal tangent is at the input pi over 3 and the output pi radical 3 plus 3 all over 3. Or you could leave it like this and that would be fine. Now we have to do the same thing for the other point. So what about when we plug in 2 pi over 3? Okay, so remember you're plugging into the original y equation. So that's radical 3 times 2 pi over 3 plus 2 times the cosine of 2 pi over 3. So we've got to keep our unit trig kind of in our mind here. So first of all, make this 2 pi radical 3 over 3 plus 2 times the cosine of 2 pi over 3. Remember in quadrant 2, it's only sine that's positive. Cosine is negative. So the cosine of 2 pi over 3 is negative 1/2. So 2 pi radical 3 over 3. This would be minus 1. And if you want to take it a step further to match my answer key, I just made 1 3 over 3. So I did do a common denominator there. So the other point is at 2 pi over 3, 2 pi radical 3 minus 3 all over 3. Or again, just use that version as well. Okay, next problem. I didn't erase my explanations for this just to save time on the video, but I will talk through this. So we're using this graph to answer these questions. Between which two consecutive points, so you can't go like A to D or A to E, consecutive points, is the average rate of change, remember that's just secant slope, the greatest. Greatest, we did this in pre-calc a lot, means highest number. So it's not always the steepest slope if some of the slopes are negative. So, all right, A to B is a steep positive slope. That would be a fairly high number. B to C would be a lower positive number. It can't be C to D because that's negative. And D to E is pretty shallow. So that's why I chose A and B. Is the average rate of change of the function between A and B greater than or less than the instantaneous, remember that's just tangent, the tangent slope at B? So you can kind of just eyeball this for one. So definitely the secant slope is larger, a larger positive number than the tangent slope. So I said secant average rate of change formula greater than derivative at B. But remember, we talked about this a lot in pre-calc, and we'll talk about it again this year. If a graph is concave down, remember that means that concave down means that the rates of change are decreasing. So yeah, the slope at A is higher than the slope at B, and that's higher than the slope at C and D because this is a whole concave down section. So it makes sense that the slope that comes before would be the higher one. A to B is a higher slope than B. And then part C was just a sketch on the graph. I erased it. So sketch a tangent line to the graph between C and D that, get these off of here, that such that the slope of the tangent line is the same as the average rate of change. So here's the average rate of change. This is leading into something we'll talk about in a couple of days, but yeah, there's a slope somewhere in here. You can kind of estimate where it is, where you've got like a parallel tangent line. So I'm saying that slope matches the C to D slope. All right, we had some of these in last night's homework. So find the average rate of change. Compare this average rate of change to the instantaneous rate of change at the endpoints of the interval. So first, let's find the average rate of change. Again, here's another pre-calc thing we did a lot. Average rate of change is f of pi over 6 minus f of 0 over pi over 6 minus 0. You need to have this formula down, and it's a really good idea to write it just so that if you keep writing it over and over, you will remember it. Okay, and then sine of pi over 6, more unit circle trig, that's 1/2. Sine of 0 is 0. This is just pi over 6 in the bottom. A little bit of fraction work here. 1/2, instead of divided by pi over 6, we'll multiply it by 6 over pi. And then 6 over 2 is 3. So the average rate of change is 3 over pi. That's the first thing I was supposed to do. And then compare this number with the instantaneous rates of change at 0 and at pi over 6. So first we need to find f prime, get an equation for instantaneous rate of change or derivative. The derivative of sine x is cosine x. And we're supposed to evaluate the derivative at each endpoint. So f prime of 0, cosine of 0 is 1, and f prime of pi over 6, the cosine of pi over 6 is radical 3 over 2. So we're supposed to compare these three numbers, which one is largest, whatever. So let's say that we're not allowed to use a calculator. They do expect you to be able to at least compare a little bit, like 3 divided by 3.14-ish is definitely less than 1, right? You have a slightly bigger number in the denominator. It's close to 1, but it's less than 1. And then radical 3, they expect you to know is 1 point, well, not 1.2, but 1 point something. And you're dividing that by 2, so that's closer to 1/2. So this is pretty close to 1. This is pretty close to 1/2. This is 1, obviously. So if I'm comparing these, I can say, okay, let's see. The smallest number is the one that's 1/2. So f prime of pi over 6 is the smallest. And then the middle number is the one that's close to 1, but not quite. So that's the average rate of change. That's f of pi over 6 minus f of 0 over pi over 6 minus 0. And that's less than f prime of 0, which was exactly 1. But remember, you can also, instead of doing this numerically, if you're not quite sure on these two, how to compare them, we should be able to very easily sketch a sine graph. There's one period of a sine graph. We're just looking between 0 and pi over 6, which is right here where the graph hits 1/2, right? So we're looking at this little interval. Again, this interval is concave down, so the rates are decreasing. So that also should help you, just like we did on the last problem. The tangent slope at 0 is the largest, and then the secant slope, and then the tangent slope at the end. So I got that both numerically and graphically for this one. Okay, a little bit of physics here. So for this exercise, we're using this position function for free-falling objects. A free-falling object means that if you're just dropping an object, the initial velocity is 0. And I'm assuming that the times are in feet per second, if I remember correctly. It doesn't actually say seconds, I don't think, in here. Okay, a silver dollar is dropped from the top of a building that is this tall. So that is our initial position. So part A says determine the position and velocity functions for the coin. So start with S of t. So the negative 16t squared is built in. The initial velocity is 0, so I'm not going to write that term. And the initial height is 1,362 feet tall. So there's the position function. The velocity function, remember, velocity is just the derivative of the position. It's s prime of t. And you don't have to write that every time. I'm just doing that for my answer keys. So if I take the derivative of this equation, I get negative 32 times t to the first, and the derivative of a constant is 0, so plus 0, or I'll just leave it at that. Part B says determine the average velocity on the interval 1 to 2. So again, if you always have a formula in your mind, every time you see average velocity, it's like, okay, I need change in position over change in time. So I need, and you can even say AROC if you want to. Our BC Calc test probably doesn't recognize that, but this is just for you anyway. So what is the average rate of change? It's S of 2 minus S of 1 over 2 minus 1. Okay, so what is S of 2? I'm going to use a calculator for these. I guess we probably could make it non-calculator, but I don't know. I used a calculator. So negative 16 times 2 squared is 4 plus 1,362. I guess this could be a no-calc problem, but that's 298. And then if I put 1 in there, negative 16, I guess I'll do this without a calculator, negative 16, so that's going to give me 1346. over 1. So I'm getting negative 48 for that. And then again, I just am assuming it's feet per second. I think that's right for that position equation. All right, that's the average velocity. Now find the instantaneous velocities at 1 and 2. So instantaneous velocity, we have a velocity equation. That just means find v of 1. So negative 32 times 1 is negative 32 feet per second. And find v of 2. Plug 2 into that, you get negative 64 feet per second. Okay, this makes sense to me too, that the first velocity, from when you drop it, the thing will accelerate as it's going down, right? So it will be gaining speed. So it makes sense that the velocity is getting larger and that the average fell in between. And then find the time required for the coin to reach ground level. So ground level is a position of 0. So we should just be setting our position function equal to 0. You could solve this graphically if you wanted, or you could, I'm just going to do algebraically. I'm sure that's faster. So 1362 divided by 16 is 85.125. Never round throughout your work, so keep all of those decimal places there. Technically, there's a plus or minus when I square root this answer, but we're talking about time, so we only are going to do the positive square root, so 9.226. So I can round at the end, 9.226 seconds is when we estimate that this thing will hit the ground. And then find the velocity of the coin at the impact. So now that I know that impact happens at this time, this is asking for what's the velocity at that time. But just be careful. It might not make a difference in this problem because velocity is just linear, but get in the habit of keeping the unrounded number on your calculator screen so that you use the most accurate version in your calculations. We don't want answers to get thrown off just because we used a rounded answer into an equation and then rounded again. So the equation is negative 32 times the time. So I'm just going to, on my screen, say times negative 32. And I get, and I get this time. So this is approximately negative 295.242. And again, I would call that feet per second. All right. I don't remember that answer, so I just want to double check. Oh, yeah, I did get that. Okay. On to the next thing. So now we're talking about another position function. This is given in meters per second, so slightly different. And this time we do have an initial velocity because we're not just dropping an object. So it says a projectile is shot upward from the surface of the Earth. So the initial position is 0 with an initial velocity of 120 meters per second. So now S sub 0 is 0 and V sub 0 is 120. What is the velocity after 5 seconds and after 10 seconds? So first let's establish our position function. So we have something to take the derivative of. So the position function is negative 4.9 t squared plus 120 t plus 0 technically. And remember the velocity equation is just the derivative of the position. So 2 times negative 4.9 is negative 9.8 times t plus 120 if I take the derivative of that. And so we are finding v of 5. I'll just use my calculator again. Negative 9.8 times 5 plus 120 is 71. Don't need an approximation there. 71 meters per second. And v of 10 should be faster. So I'm just going to grab this equation and insert a space so I can do 10, or you could just retype it. So I got, I guess it doesn't have to be going faster because maybe over this span of time, I forgot, we're shooting upward. So we're probably reaching the peak and you slow down before you come back. So not faster, my mistake. 22 meters per second. Like if you shoot something up in the air, when it changes direction, it's going to slow down and then come back faster. All right. For this section, I did not erase my graphs here, but we've done this a few times. So this graph represents the distance in miles a person drives during a 10-minute trip to work. Make a sketch of the velocity function. So remember, velocity is just slope of a position graph. So I just found the slope of each section. So slope is 1/2 here. So I should have a constant velocity of slope at 1/2 right here. Slope is 0 between 4 and 6, 0. Slope is 1 from 6 to 10, so I kept it at 1. So I did that for each one. 102, the slope was 5/6. So I made on my chart here, I put 1 up here, and then I put, there's 6 little tick marks to get up to 1. So that's how I did 5/6 for that slope. And then a slope of 0, and then a slope of 1/2, which would be like at the third 3/6 tick mark. And then we go the other way. So we did just 104 here. Now you have velocity, so find position. So again, we're starting at 0. You haven't traveled any distance when you're first starting out. The area underneath the velocity curve is 30 times 4, so 120 miles have been traveled. So you should reach a height of 120 wherever you mark that. And then you're stopped for a while. So no change in position for a little while. And then you gain 240 more miles. This is a huge commute to work. Are these are miles? Yeah. Okay. So I don't know about that 10-minute drive to work. Like that's kind of crazy. But anyway, so then you gain up to 360. Yeah, these are miles per hour. Oh, miles per hour times minutes. Okay. That's making more sense. I'm going to need to adjust this here. So, okay, ignore my positions here. I will come back. Excuse me. I will come back and fix this one. I was like, wait, whose commute is 360 miles? That's like across a state. Okay. I'm going to change these speeds to miles per minute. And then we can go from there. So like 30 miles per hour, 30 miles in 60 minutes. This is going to make a lot more sense. That's a 1/2 mile per minute, right? Okay, so that's much better. So let's change that. So now the velocity graph is like, okay, you're at 1/2, 1/2 of a mile for 4 minutes. That's a lot better. That's 2 miles. And then we're still at 0. And then from 6 to 10, so 60 miles per hour. So 60 miles in 60 minutes is 1 mile per minute. So then we have a height of 1 for 4 minutes. So 1 mile for 4 minutes, that's a total of 4 miles. So much better. I wasn't really thinking about that when I did it. Okay, so let's fix this. So from 0 to 4, we need to travel 2 miles. Makes more sense. Like that. And then from 4 to 6, we're still going to flatline. And then from 6 to 10, we should be gaining 4 miles. So 4 miles above 2 miles is up to 6. There we go. That's a much better position function. I will fix the key that I post for that. Okay, now what about this one? This takes a bit of thought too. So find A and B such that f of x is differentiable everywhere. So remember what that means. The first thing is if f is differentiable everywhere, especially at 2 where this breaks, we need to make sure that f is continuous everywhere. So we have to make sure that's true. And then the other thing is that if f is differentiable, it means that if you have an f prime graph, that f prime graph must be continuous. Because remember, it's where the f prime graph has a jump, where you have like a sharp turn or if the f prime doesn't exist somewhere, then that can't be differentiable. So, okay, so let's start with the first thing. F is continuous if we can show that f of 2, the function value, is equal to the limit as x approaches 2 of the function. So start there. All right, so f of 2 would be me plugging 2 in for x in the top part. So a times 8, right? So 8a. And then the limit would be me plugging 2 in for x in the bottom part. So 2 squared is 4 plus b. And then I'm kind of stuck right here because I have a 2-variable equation and nothing else to do with it. So that's where the second part comes into play. I need to know that f prime is continuous. So first I need to make an f prime equation. So take the derivative of each piece. So the derivative of ax to the third would be 3a times x squared. A is just a constant. So that's for x values less than or equal to 2. And then the derivative of x squared plus b, the derivative of x squared is 2x. The derivative of b, which is a constant, is 0. And that's for x greater than 2. So f prime is continuous if f prime of 2 is equal to the limit as x approaches 2 of f prime of x. All right, so f prime of 2 is plug 2 into the top equation for x. So 3 times 2 squared is 12 times a. The limit for f would be plugging into the other piece. So plug 2 into 2 times x, that's 4. Divide by 12. 4 over 12 is 1/3. So here's a. And then this is where you had an expression relating a and b. So now I know that 8 times 1/3 is equal to 4 plus b. 8/3 minus 4, so minus 12/3 should equal b. So negative 4/3 is equal to b. All right, that's a pretty good problem. Here's a pretty common AP problem where they give us information rather than an equation and ask us to work with derivatives. So this says find f prime of 2, and here's some information. We're just doing 105. F of x is 2 times g of x plus h of x. Take the derivative with respect to x. So f prime of x is equal to 2 times g prime of x plus h prime of x. So you're allowed to take the derivative of each term. And we're supposed to find f prime of 2, so that would mean 2 times g prime of 2 plus h prime of 2. And if this is a free response question, which it often is part of one, you've got to show this work. Don't just do everything in your head and give an answer. You usually get credit for this line, and then you're doing the rest of the work here. So 2 times g prime of 2 is negative 2 plus h prime of 2, which is 4. Negative 4 plus 4 tells me that f prime of 2 is equal to 0. All right, last set of problems. I did not erase my work for this. We have the graphs of f, f prime, and f double prime. And I did not label them on here because it's hard to distinguish, but remember the way derivatives work. The second derivative will need to be, oh, I'm sorry, I have this backwards. Remember the way this has to work. I wrote it backwards. The first function has to be the highest degree because then you're going to use power rule and the degrees will keep counting down. So the original function has to be the cubic, and then the first derivative will be quadratic, and then the second derivative will turn out linear. All right, same thing here. The first original function has to be the highest degree, so it's got to be quadratic. You take the derivative of a quadratic and you get a linear. You take the derivative of a linear and you get a constant. All right, that's it for this homework assignment. Please let me know if you have any questions.